All right, so this is now the opposite case where instead of having our voltage source over here and our known value for V1 and trying to determine the induced voltage V2, we now have a voltage V2, which obviously drives a current I2 through this second coil here. Again, we'll call this L1 and we'll call this one L2 right here. And we're driving a current through this coil L2, which of course induces a magnetic field. These magnetic flux lines link the two coils, or specifically these magnetic flux lines link the two coils. And we get some induced voltage V1, and we want to determine the expression for that voltage. Okay, so I'm going to go through this derivation again. It's almost the exact same derivation, starting with these fluxes. Of course, the flux, the total flux through coil 2. Here is going to be the flux that's linking coil 2 to itself, plus the flux that's linking coil 2 to coil 1. Okay, which is exactly what we did in the previous case. We started with that. And then we need to look at this magnetic flux linkage term here, lambda 2, which is going to be equal to the number of turns of coil 2 multiplied by the total flux linking coil 2, which is the one that we just wrote down here. Okay? We know that the lambda 1 then is going to be the number of turns of coil number 1 multiplied by the flux linking coil 1 to coil 2, which in this case is phi 2, 1. And so we're kind of right back where we started. Let me move these over. And so from here, we kind of wrote the self-inductance of coil 1. In this case, we're going to write the self-inductance of coil 2, which we know very easily is equal to lambda 2 divided by current number 2, I2, which is what we're looking at here. Okay? And lastly, we know that the voltage, V2, in this case, is going to be equal to the rate of change of lambda 2 with respect to time. And of course, if we, if we rearrange lambda 2 here, we can get lambda 2 is equal to L2 times I2. And we can rewrite this expression as L2 times di2 dt, which is exactly what we would expect for the voltage across coil number 2. With a current flowing through it, it should be the inductance L2 multiplied by the rate of change of the current through that inductor. Okay. Similarly, we have an open circuit here on the V1 side, so there can be no current flowing through L1, so it doesn't make sense to write L1 in terms of I1 here because I1 is 0. So instead, we should start by writing V1 is equal to the rate of change of the magnetic flux linkage lambda 1 with respect to time. And so then we write this again as N1 times d phi 2, 1 with respect to time. And because we know that this current here was induced, or sorry, this flux here was induced by current I2, we can rewrite this as N1 times d phi 2, 1 di2 multiplied by di2 dt. And again, we kind of match forms here. We've got V2 equals L2 times di2 dt, and we're looking for V1, which instead of L2 here, we have this term here, which is also going to be in units of henries, multiplied by di2 dt. And so out pops our mutual inductance M12 here. The mutual inductance of coil 1 due to the current I2 is going to be equal to M1 or N1 times d phi 2, 1 di2. And I think that this stuff's going to make a lot more sense once we start doing example problems. Right now, I'm just deriving the mutual inductance. And so you see that the mutual inductance here is derived by just kind of carrying out this analysis of the flux linkage between the two coils, looking at the flux lines. And what we're really going to end up with ultimately is not circuits that have an open on one side like they did here or here, but rather we're going to end up looking at circuits that have something going on both sides. Maybe a resistor here, a coil here, some kind of other coil here, maybe another resistor here, and then, you know, we could have anything here, maybe another source. And so now we have to figure out how to solve this circuit. And what's going to happen is this source on the right is going to drive a current through this inductor on the right, L2, which is going to give rise to some current in the inductor on the left. But then the source on the left is going to drive a current through L1, which is also going to drive a current through L2. And so we need to keep track of all of that when we solve these circuits. And it does get a little bit confusing. And so up to this point, all you should really kind of have in your head is that we need to account for this, okay? It's not 100% important that you understand this derivation. I like to derive equations so you know where things are coming from. But again, when we're looking at circuits, I'm not gonna sit here and ask you to derive that. I'm just gonna give you the mutual inductance between the two coils, M, and I'm gonna expect that you know how to deal with that, because I'm gonna teach you how to deal with that as we move along in this module, okay? So the derivations are great. If you have any questions about the derivations, please feel free to ask. Obviously, there's a lot of derivatives here and some canceling and some maybe some hand waving, but what we're really trying to get to is to be able to solve circuits like this that have a mutual inductance linking the two coils together, and to determine how to account for this, okay? Because up to this point, we would not have seen these two circuits and known that they had anything to do with one another if they weren't connected physically. But because they are connected through magnetic coupling, we have to know how to account for that. Okay, so that's what we're going to get into next. I've kind of derived the mutual inductance and what it is, just basically shown that it is a term that pops out of the math that can be treated as an inductance because it has units of henries. And we're going to basically utilize that to help us solve these circuits, okay? So I'm going to end this video, and let's see, what do we got in the next video? In the next video, we are going to talk about the coupling coefficient, okay? So the coupling coefficient basically tells us how tightly these two coils are coupled, and we'll talk about that in the next video. It's also really important for building these circuits in LT Spice. So I'll end this video here, and we'll see you in the next one.